All right, so this is definitely a little bit more involved of an example. You know, we aren't looking at two separate loops here. We're looking at one circuit that is electrically coupled and magnetically coupled. Okay, so here, you know, we have these two coils that are not electrically coupled, but they're only magnetically coupled, right? They're not connected to each other, but the magnetic fields are, you know, coupling them. That's what we talked about a lot in this module so far. This is a circuit where they are electrically connected to each other, and we have the effects of magnetic coupling. So nothing really changes, but it definitely looks a little bit different than what we've seen in the last two examples. Okay, so let's go ahead and work this one out. It's definitely going to take us a little bit longer. Might take 3 or 4 videos to get through this one, but I want to make sure that we do it right. Want to make sure that we thoroughly cover how to take care of the dot convention and the mutual inductance here. There's also something called magnetizing inductance. That's why I keep tripping over my words here. Mutual inductance and magnetizing inductance are not the same thing, but they are both relevant to this topic. We're probably not going to get into magnetizing inductance in this class. It's a little bit beyond the scope of EE 221. However, all right, let me stop babbling and let's get into this example. So we're given, well, what we want to find is find average power. Okay, so now we're pulling some concepts from Module 3 into this problem. Find average power delivered to RL. And they say that we want to do this for 3 different values of for 3 different values of mutual inductance, okay? So for part A, they say let M equal 4 millihenries. For part B, they say let M equal 1 millihenry. And for part C, they say let M equal 0 millihenries, which basically means that there's no coupling at all. And so for case C, we would basically just be solving the circuit as if there were no coupling whatsoever, and this was just a standard 2-loop circuit. So, but that's not a very interesting case for us. We're interested in solving this for parts A and parts B, or parts A and B. And they've already put it in the phasor domain for us, which is nice. So let's go ahead and just redraw it with the dependent sources that we know we're going to get here. So, of course, I'm going to have this phasor Vs. I'm going to have an impedance R1. I'm going to have an impedance for this first inductor. And then in series with that, I'm going to have the voltage source, which is induced by L2, basically here. We don't know the polarity yet. And then in this middle part, we're going to have an inductive impedance here. And of course, we're going to have a dependent source here. This one looks pretty bad. It's supposed to look more, square. That's not too bad. And so this is my circuit, just like this. Okay, so let's plug some values in here. What do they give us for the frequency? They tell us it's 60 hertz. So I didn't write any of the values here. F is 60 hertz. They give us that RL is 10 ohms. They give us that R1 is 5 ohms. They give us that L1 is 10 millihenries. L2 is 30 millihenries. Again, they're giving us pretty realistic values here. And then Vs is 30 angle 60 degrees volts. Okay, so those are the givens for this problem. And so we need to go through and figure out these impedances. So R1, of course, is just going to be 5 ohms. RL is 10 ohms. That's out here. J omega L2, let's throw that in my calculator. 2 pi times 60 L2 times 30 times 10 to the minus 3. I get J 11.31. Okay, so that's for J omega L2. How about J omega L1? It should just be a third of that. So I'll divide by 3 and I get J 3.77. Of course, this is just 30 angle 60 degrees volts. And now we need to determine the induced voltage source values and their polarities, okay? So let's just start with, let's just keep everything in terms of M so that when this problem's all said and done, we can just plug these 3 values in for M, and then we can go from there. Then we don't need to solve the problem 3 different times. We can just keep it in terms of M, and then we can plug in 4 millihenries, 1 millihenry, and 0 and see what the average power is. So we'll keep everything in terms of M. So of course we know that we're going to multiply by J times 120 pi times M, but then we need to multiply by the current that induced that source. The question is, what current is that? Here we're going to have J 120 pi times M. If you're wondering where 120 pi came from, it's 60 hertz times 2 pi. And so let's take a look at this. We've got current flowing here, I1. That's the current that's going to induce this voltage source, right? This voltage in the second coil. Okay, so for that one, all I need to put is I1 multiplied by J times 120 pi times M. But what about the current that induces this voltage source? That's the current flowing through V2, right? Well, what current is that? That's I1 minus I2, right? There's 2 currents flowing here. I've got I1 flowing into this way, and I've got I2 flowing into this way. So what I need to do is I need to account for both of those when I write this mutual inductance, because it's not just I1 or just I2. It's actually a combination of I1 and I2. So from the perspective of the second coil, we're going to have to take a look at how that shakes out so that we get this polarity right, and so that we can determine whether this is going to be I1 minus I2 or I2 minus I1. And so we're going to stop this video here since it's got a little bit long. But in the next video, we'll determine this current, we'll determine these polarities, whatever they may be, and then we can move forward with solving this problem. All right, let me go ahead and just label these currents. This is going to be called I1. They're calling this I2. And in the next video, we'll go ahead and move forward with this example problem. All right, so I'll end this video here.